A 15 kilogram block of metal is pulled with the forces shown in the diagram on top of ice. Well, if it's on top of ice, we assume that it's going to be no friction. And what we've got to do is determine the resultant force acting on the block and its acceleration. Now, we have the two forces acting on the block and they're at an angle to the block. So our first job is to find the component of this force vector which lies in the horizontal direction. I can draw it in like that, and that's the horizontal component of it. And also there's going to be a horizontal component due to this other vector here, which is identical in magnitude and size, and I can draw that one in as well. So there's the two horizontal components of these two forces. So all I have to do is work out the horizontal component of one of the forces and just double it to get the resultant force. So we know in this case we have got the following situation. We have got 100 newtons at an angle of 30 degrees. So therefore the horizontal force acting on it will be 100 times cos of 30 degrees. If you're not sure, you can work out a little triangle and say that the angle here, there's the opposite side and that's the adjacent side. So it's got to be the adjacent side you've got to use. That's got to be cos. But remember, cosine of an angle is equal to the adjacent over the hypotenuse. So you get plenty of practice doing that. But you know, if you're looking at the horizontal components, it's always going to be cos 30 degrees because it's on the ground. O on the ground. So that's the value for the component, the horizontal component of the top vector. And the bottom one is going to give the exact same value as well, 100 times cos 30. Exactly the same horizontal component size. So we just add those two together and the resultant force is going to be equal to 100 cos of 30 degrees plus 100 cos times 30 degrees. And if we do that in a calculator, we end up with a value equal to 173 newtons. So we know there's going to be a forward force, a resultant force of 173 newtons acting on that block. To work out the acceleration of it, we know fine well the famous acceleration law from Newton's second law. The acceleration is the unbalanced force divided by the mass. And we know it's going to be an unbalanced force of 173 newtons. There's not going to be a backward force because we're on ice with no friction. So we have 173 newtons and we're dividing that by a mass of 15 kilograms. So we work that out, we get an acceleration of 11.5 meters per second every second. Remember the units for that. So the key to doing this type of problem is you have to find the component of the force vector in this direction. That'll be this one here, and the one down here as well. It's exactly the same, so it's the same angle and same size. And we just do the same thing again, 100 times cos 30, 100 times cos 30, add them up and we get the resultant force. And then we know how to work out the unbalanced force because there's no backward force acting on it. So it's going to be just simply 173 newtons and the mass is 15 kilograms, which gives us the acceleration. A 5 kilogram block of wood accelerates down a slope. The force of friction acting on the block is 4.5 newtons. And we have to determine the component of the box's weight acting down the slope, and we've got to also determine the acceleration of the block down the slope. Well, we know from our formula, and we know from our formula sheets, that the force down the slope, the component of weight down the slope, is going to be of the following value. mg, the weight, times sine of 30 degrees, always acting down the slope. That's the component of weight acting down the slope. So we can work that out. It's quite simple to do. The mass of the block is 5 kilograms. G is going to be 9.8 for the planet Earth, and sine 30, and that is a well-known friend, that's going to be equal to a half. So we work that out in a calculator, we end up with a value of 24.5 newtons. So it's going to be 24.5 newtons acting down that slope. So 24.5 newtons. Now we're also told that there's going to be a force of friction acting on the block, so we have to draw that in as well. We just draw a backward arrow to show that the force of friction always acts opposite the motion. And we don't need to worry about scale at the moment because we're told it's going to be 4.5, just to give yourself a mental picture of what's happening. And that is the backward force, 4.5 newtons. So now we can see the diagram very clearly, and that's why it's so important to draw in your vectors. Don't have to be to the same scale, just to give you a mental picture of what is happening. So we have 24.5 newtons pulling the blocks down the slope, and we have got 4.5 newtons of friction holding it back. So we can then work out what the unbalanced force is. It's quite simple. The unbalanced force is going to be equal to, since it's going down the way, 24.5 newtons. Take away what's holding it back, 4.5 newtons. So that's going to give us an unbalanced force of 20 newtons. So bingo, we have got the unbalanced force, which I'll draw as a two little lines like that, of 20 newtons. So that's going to be the unbalanced force. To find the acceleration of the object, it's quite simple to do. We just do the following. Acceleration is the unbalanced force acting on the object divided by the mass of the object. In this case, it's going to be 20 newtons divided by the mass of the object, which is going to be 5 kilograms. In this case, so we put in 5, and we're going to have an acceleration of 20 divided by 5 is 4 meters per second every second. Remember the units. And that's how you do that diagram. The key to that one is knowing that the component of weight down the slope is mg sine theta, and also drawing the force diagram to have a mental picture of the forces acting on the block. Then find unbalanced force. You're home and dry. You can find the acceleration. An 8 kilogram dog stands on scales in a lift. The lift accelerates upwards at 1 meters per second every second. And we've got to determine the reading on the weighing scales. Well, remember, the reading on the weighing scales is a measure of how much the floor is pushing up on you. So there's two forces acting on that dog. We can draw them in, and the forces are as follows. We can draw them in like this. We have got the dog's weight acting straight down, and also we've got the force of the floor pushing up on the scales, which is this force here like that. Remember, that's the support force, or as we call the normal force. Normal force is called normal because it's always at right angles and it's pushing up onto the scale. And it's this floor pushing up onto the scale which makes the scale read what is the weight of the dog. So we can then put in our numbers. So we can put in the following. We have got for the dog is weight acting down the way, and we've got the normal force pushing up the way. Now remember, the normal force is the force which is supporting the dog. It's pushing up on the dog. If that floor wasn't there, the dog would accelerate downwards towards the centre of the earth. So there's the two forces acting on the dog. Now, because we're accelerating upwards, we've got an unbalanced force, and the unbalanced force is going to be accelerating upwards like that. So we go to the side of our page and we put down what the unbalanced force is going to be. All the forces acting up the way, that's the normal force pushing up on the dog. Take away the weight of the dog acting down the way, and that should give us the unbalanced force acting on the dog. The normal force is N, the weight is mg, so we take away mg, and we know that the unbalanced force is always going to be equal to the mass and its acceleration. Now a little bit of rearranging here to get the normal force on its own. N is equal to, and we take mg over the other side, add mg onto both sides, so we get N equals mg plus ma. So what we're seeing here is that the normal force, the force pushing up, the floor pushing up on the dog, is actually equal to the dog's weight plus the mass times acceleration of it moving upwards. So we can put in our numbers now. We can say that the normal force, which is going to be the reading on the scales, remember, is going to equal to mg, which is going to be 8, put a bracket around this, 8 times 9.8, and we're accelerating upwards, so it's going to be plus 8 times, and we're accelerating upwards at 1 meters per second every second. We get that. So we do that in a calculator, we end up with the dog's apparent weight is 86.4 newtons. Now I say the dog's apparent weight, but it's not really the actual weight of the dog, because the weight of the dog is fixed. It's always equal to mg. That never changes, but it's the push on the floor that changes. Now if you're accelerating up the way, think of the floor pushing you more, and if the floor pushes you more, it's going to push the scales more, and therefore give a bigger reading on the scale, 86.4 newtons. And likewise, if you're accelerating downwards, then the floor is going to have a less push on you, and therefore you're going to feel lighter. But you're not really, because your weight stays the same, but the reading on the scales will appear lighter. So that's the formula you must really remember, and you must remember how we get to that formula, because this formula is not going to be put into your relationship sheet. So it's better to draw the diagram out and show the two forces, the weight pushing down on the floor and the normal force pushing up on the floor. This is not a Newton's third law, because what I've got here is the floor itself pushing up on the dog. So that's the two forces. We have an unbalanced force. We go to that situation here. Unbalanced force is N, take away W. And we can rearrange to get that famous equation here, which is really the reading on the scales equation, which is the normal weight, the actual weight of the dog, plus whatever the acceleration is times its mass. So to answer this question, the dog, the scale reading will be 86.4.